Section 7.7 Improper Integrals. In this section, we extend the concept of integral to the case where the interval of integration is infinite, and also to the case where the integrand is unbounded at some point on the interval of integration. These are called improper integrals. We have defined the definite integral from 1 to 3 of 1 over x squared dx on a closed bounded interval 1, 3. Then what about the integral from 1 to infinity of 1 over x squared dx? In physics, economics, probability, and statistics, it is useful to have a concept of an integral that is defined on the entire real life or on half-lives of the form x is greater than or equal to a, or x is greater than or less than a. To find such integral, first use a definite integral to compute the area from x equal a to some finite number x equal n, and then let n approach infinity in the resulting expression. If the limit is finite, then we say that the improper integral converges, otherwise the integral diverges. We take an example of a convergent improper integral. Evaluate the integral from 1 to infinity of 1 over x squared dx. We begin by computing the integral from 1 to n. It equals minus 1 over n minus 1 over 1. Then we take the limit as n tends to infinity to obtain 1. Thus, the improper integral converges and has the value 1. We take another example. Evaluate the integral from 1 to infinity of 1 over x dx. We compute the integral from 1 to n and let n go to infinity to obtain infinity. The limit is not a finite number, which means that the improper integral diverges. We have shown that the improper integral from 1 to infinity of 1 over x squared converges, and the improper integral from 1 to infinity of 1 over x diverges. In geometric terms, this says that the area to the right of x equal 1 under the curve y equal 1 over x squared is finite, while the area under the curve y equal 1 over x is infinite. The reason for the difference is that as x increases, 1 over x squared approaches 0 more quickly than does 1 over x. Note that if the integral is going to converge, the function must approach 0 at infinity and its value must get small quickly. By mathematical reasoning, we can prove that the integral from 1 to infinity of 1 over x to the order of p converges if and only if p is greater than 1. Using this fact, we know immediately that the integral from 1 to infinity of 1 over square root of x diverges because p equal 1/2 and less than 1. If we evaluate the integral between 1 and n and let n approach infinity, we obtain the result of infinity. Now we are going to examine the second type of improper integral. For example, evaluate the integral from 0 to 1 of 1 over x minus 1. In this example, 1 over x minus 1 is a function that is continuous on the open interval 0 to 1, but is unbounded at the right endpoint 1. We can replace 1 by n We are going to examine the second type of improper integral. For example, evaluate the integral from 0 to 1 of 1 over x minus 1. In this example, 1 over x minus 1 is a function that is continuous on the open interval 0, 1, but is unbounded at the right endpoint 1. We can replace 1 by n, evaluate the integral, and take the limit as n approaches 1 from the left. The value of the limit is minus infinity, which means that the integral diverges. The third type of improper integral appears when both of the limits are infinite. For example, the integral from minus infinity to infinity of 1 over 1 plus x squared. To evaluate this integral, we separate it into two improper integrals, one from minus infinity to 0 and one from 0 to infinity. For the first integral, we evaluate its value from m to 0 and then let m tends to minus infinity. For the second one, we replace infinity by n and take the limit when n goes to infinity. The values are 0 minus pi over 2 and pi over 2 minus 0 respectively. So the result is pi. An interesting geometric figure is Gabriel's horn. This is a solid generated by revolving about the x-axis, the unbounded region, under the curve y equal 1 over x for x greater than or equal to 1. This solid has a finite volume but infinite surface area. An interesting geometric figure is Gabriel's horn. This is a solid generated by revolving about the x-axis, the unbounded region, under the curve y equal 1 over x for x greater than or equal to 1. This solid has a finite volume but infinite An interesting geometric figure is Gabriel's horn. This is a solid generated by revolving about the x-axis, the unbounded region, under the curve y equal 1 over x for x greater than or equal to 1. This solid has a finite volume but infinite surface area. We will use improper integrals to prove these facts. We will find the volume by using disk method. The result is pi. The surface area is calculated by the integral from 1 to infinity of 2 pi multiplied by 1 over x multiplied by the square root of 1 plus minus 1 over x squared, and this integral diverges. The interpretation of these results is that you can fill Gabriel's horn with a finite amount of pen, but it takes an infinite amount of pen to color its surface. Sometimes it is difficult or even impossible to find the exact value of an improper integral. Yet, it is important to know whether or not it converges. In those cases, the comparison test may be useful. It is stated for the improper integral of first type, but a similar version for the second type can also be stated. Suppose f and g are continuous functions such that 0 less than or equal to f less than or equal to gx for all x in the open interval from a to infinity. If the integral from a to infinity of gx converges, then the integral from a to infinity of fx converges. If the integral from a to infinity of fx diverges, then the integral from a to infinity of gx diverges. It means that to show that an integral is convergent, we show that it is less than a convergent integral on the same interval, or else an integral is divergent if it is greater than a divergent integral. We take an example. Show that the integral from 3 to infinity of 1 over square root of x minus 1 diverges. We can evaluate this integral directly, but we can prove that it diverges by showing that it is greater than a divergent integral. Note that 1 over square root of x is positive and is less than 1 over square root of x minus 1. And the integral from 3 to infinity of 1 over square root of x diverges because it has the type 1 over x to the power of p, where p equals 1/2 less than 1. Therefore, according to the comparison test, the integral from 3 to infinity of 1 over square root of x minus 1 diverges. Now, we show that the integral from 3 to infinity of 1 over x squared plus 1 converges. Note that 1 over x squared plus 1 is positive and is less than 1 over x squared. And the integral from 3 to infinity of 1 over x squared diverges. Note that 1 over x squared plus 1 is positive and is less than 1 over x squared, and the integral from 3 to infinity of 1 over x squared converges because p is equal to 2. Therefore, the integral from 3 to infinity of 1 over x squared plus 1 converges. This is the end of section 7.7. Thanks for watching.